All right, here we've got a shell sphere for the next in our Gauss's law practice series. Okay, I've already drawn the shape. Boom. The electric field. So the electric field will be pointing outwards from this thing. Boom. Okay, this includes towards you and away from you as well. All nice and perpendicular to the surface. That's our electric field for you. Gaussian surface. The Gaussian surface needs to enclose the uh, charge in question. So here's my Gaussian surface. It is a sphere larger than the actual sphere. Okay. The actual sphere has a radius of capital R. I'm using capital here to denote that it's a constant, as I try to make sure that I'm using constants as capitals. And if something's a variable, like I could have had the radius of the Gaussian surface be out to there, or it could have been out to here or here without fundamentally changing anything. So R is a variable in this case. Here's my Gaussian surface. Boom. The area of the Gaussian surface. Well, the area of a sphere is equal to 4 pi r squared. Okay, that's just something worth memorizing. It's also something I put on my midterms equation sheet. Always worth putting there. Next, how much charge is enclosed? The charge that's enclosed is only along the surface. It's not inside the entire thing. So this is a surface charge density. As a surface charge density, we have sigma is equal to Q divided by the area. And in this case, Q enclosed will be sigma multiplied by, note that the area is only out to the black surface there. So that's 4 pi capital R squared. That's a distinction that's really important to get. Many times you'll use the same equation but plug in different values for problems like these. So the fact that one area is out to the radius of the object, whereas the Gaussian surface is to a different area, in this case a different radius, in this case a larger radius, it's important to distinguish that. Q enclosed, determined. Solve for the electric field. E A equals Q enclosed over epsilon naught. And that's the area of the Gaussian surface. The electric field multiplied by 4 pi lowercase r squared is equal to sigma 4 pi capital R squared divided by the permittivity of free space. Got some redundancies here. Boom. Therefore, the electric field is equal to sigma capital R squared over epsilon naught little r squared vector. Okay, this is very much so like the electric field near a point charge. Okay, I'm going to add outwards. Okay, I'm going to do 2 follow-ups with this. Previously, we've had that the electric field outside of a point charge or sphere is equal to k q over r squared. in the r direction, which is what outwards is. Okay. Are these the same? Well, to figure that out, I'm actually going to use this equation. And instead of canceling out like I did earlier, I'm going to say the electric field is equal to sigma 4 pi r squared, and put a parentheses around that, divided by, keeping this 4 pi here, 4 pi epsilon naught, then the r squared. Remember that k is equal to 1 over 4 pi epsilon naught. Forgot my r hat, sorry about that. So we get the electric field is equal to 1 over 4 pi epsilon naught. That's k. The whole parenthetical there, that is the charge enclosed. And we're just left with r squared in the denominator, r direction. Same. Okay. Big advantage of this, you can find the electric field in different ways. Say you don't know the total charge, you just know the size of the sphere, the charge density, and the radius out that you're considering. You can still find out the electric field without trying to do an additional calculation for the total charge. Okay. One more thing, we're not done yet. We didn't do inside. I'm going to save that for the next video. On the next video, it'll be the same thing, but what about inside the shell? And that'll be a short video.